Faults also aren't always straight lines. They bend. They change what their dip is. We call this a listric fault when it has a concave upward shape. So basically it starts more steeply near the surface, and as it goes deeper it curves and eventually may end up horizontal. Listric faults are very common and happen in extensional zones, and we can get something like we see here on the right, where we have a series of them, and it usually ends with a little rollover anticline. You can see one here on the right, you can see one here on the left. Basically, as the extension happens, some of the rock slumps down and we get this little anticline. Listric faults can also happen at very small scale, so it doesn't have to be mountain-sized. Here we can see a lens cap of a camera for scale, and we have little tiny listric faults. Sometimes the faults change more abruptly. They'll have sections that are horizontal, running either through a bed or between beds, with then sections that cut up across beds. So these parallel areas are called flats, and the sections that cut across beds are called ramps. And we can have a whole series of ramps and flats. Sometimes in strike-slip faults, like the San Andreas Fault, it's again not a perfectly straight line. So there are places where when you have the bend in the fault, it's getting squished together. It's a restraining bend. You can see here in image A, as those blocks try to move, it's smashing the area in the curve tighter and tighter. On the other hand, you can have it where the bend is going in the opposite direction, like in block diagram B there, and you can see it's stretching and ripping as it extends. It's a releasing bend. The blocks are pulling away from each other. The two terms that we can use for this are transpression and transtension. Transpression is when in a strike-slip fault we have compression in a restraining bend. Transtension is when the strike-slip motion results in extension, the releasing bend. We'll see some photos of these coming up shortly. Now, the last thing to talk about before we start getting into some real-life images instead of little cartoon drawings is how a fault can terminate, how the fault ends. There's a few different ways shown here. They can reach a surface, either the ground surface, like right up here where the capital A is, or the surface of the sediment hitting like an igneous rock body. So the fault ends at the end of the sedimentary layer, or even an erosional surface that used to be a ground surface. They can splay into smaller faults, releasing the stress, or they can merge. So you can see here in the bottom diagram that there are faults reaching the ground surface, and then at the other end they're all merging down together. Sometimes faults reach the surface and we see them. Other times they're completely underground. They're called a blind fault. There's no way to tell, looking at the ground, that there's anything going on. The only way we can find out is either getting down into the ground, drilling, excavating, road cuts, etc., or through geophysical surveys, doing like a seismic survey, a resistivity survey, different kinds of things that you can learn about if you take a geophysics class. Now, getting into real images again, one of the things that can happen in a fault zone is the rock can get shattered. Faults are violent places, so it's no surprise that the rock gets broken up. Brittle fault rock breaks into jagged fragments. It's not traveling, it's not getting weathered, it's just getting broken. So we have lots of sharp angles. It can be cohesive or non-cohesive. So maybe it's freshly broken and really loose and gravelly. Maybe it shattered a long time ago and it's reformed into rock. They're both possible and happen in different faults. When it has become cohesive again and creates a rock full of angular bits of rock, we call it a fault breccia. If you remember back to your introductory class, a rock made of angular fragments of rock is called a breccia. If it's made in a fault, we call it a fault breccia. You can see in this image, for example, there's a little Swiss Army knife, pocket knife for scale. So some of these pieces are pretty small, some of them are multiple inches across. Sometimes in a fault there can be so much pressure and stress that it's creating heat and can melt some of the rock. So it can break the rock, sometimes it can even melt some of the rock. Not all of it. It's not like you've got magma inside the fault zone, just because of fault movement, but it can melt some of it. And so we get something called a pseudotacholite. It's glass-like rock that forms when frictional sliding makes the rock hot enough to melt. Now, the fact that it's glass-like suggests that it melted and then cooled very rapidly. So it only got hot enough briefly. It didn't have time to crystallize. So probably there's big fault movement, lots of friction and heat briefly, and then it's cooling down as the heat dissipates into the country rock. We can also get something called argile scagliosi. Kind of fun to say. This is just strongly foliated rock that is clay rich, or at least very fine grained, so clay and silt. Strongly foliated because of the stresses that are building up within that fault zone, and then this movement that'll happen continuously in the same direction results in strong foliation. Now, slick and slides. I love the term slick and slides because it reminds me of being a kid and having a slip and slide, and to a degree it's kind of the same idea. You continuously slide down your slip and slide. It's a nice slick surface. Well, in a slick and slide, it's a fault surface that's been polished smooth by continual sliding. Almost looks like you could spray it down with a hose and do a belly flop. Key thing is almost. You probably would only try that once and end up in the hospital because this is rock. It's not a soft, grassy lawn. But It's a nice smooth surface, polished by frictional sliding in a fault. Slip fibers. We can have a fault that has some of that transpression and transtension, and in the transtension curves we don't actually get gaps. It's going to get filled in. Sometimes if that fault is moving very slowly and it's filling in very slowly with crystallization and deposition out of water, we can get fibrous growth in that fault zone. The fibrous growth is in line with the fault displacement in the transtensional areas where there's extension. And then sometimes, millions of years later, there can be erosion that exposes it, and then you have this fibrous rock exposed at the surface, which you can see in the bottom here. So basically, oops, the top here is like time 1, in the middle here is time 2, some point after time 1, and then at the bottom is time 3, far into the future, after all the growth and erosion. And actually, this image is too grainy. Never mind. An echelon. Repeating pattern. We've seen this when we were looking at joints. We saw this when we were looking at veins. Here, again, it's veins because it's filled in with a mineral deposit. But this an echelon vein is actually from a fault. There were tensile fractures along a fault, creating an echelon joint array. We had talked about how you can have joints along a fault, and this is one of those examples. In this case, the fault was kind of running top left to bottom right, and then there are these 1, 2, 3 an echelon joints.